Hello everyone, and welcome to AISC's Night School, Introduction to Steel Bridge Design. Today is August 8th, 2016, and this is Session 4, Loads and Analysis, presented this evening by Dr. John Kulicki of Majeski & Masters. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce this evening's speaker. Dr. John M. Kulicki of Majeski & Masters in Mechanicsburg, Pennsylvania is tonight's speaker, where he is the Chairman Emeritus and Senior Technical Advisor. A graduate of Lafayette College and Lehigh University, Dr. Kulicki has more than 40 years of experience in bridge analysis and design. During his time with Majeski & Masters, Dr. Kulicki has worked on numerous flagship bridge projects, including the second Blue Water Bridge in Port Huron, Michigan, the Quincy Bayview Bridge in Quincy, Illinois, and the recent main span design for the new I-74 Quad City Bridges. Dr. Kulicki's contributions and dedication to the engineering community has been well recognized throughout his 40-plus years of involvement. Just to name a few of the many awards he's received, in 2001, he received a special citation from NSBA, and that was followed in 2002 by a Lifetime Achievement Award from AISC, as well as the Engineer of the Year Award by the Pennsylvania Society of Professional Engineers. And in 2002, he became just the 11th engineer in 70 years to receive the prestigious J. Lloyd Kimbrough Award from the American Institute of Steel Construction for his achievements in bridge analysis and design. We're very pleased to have Dr. Kulicki this evening presenting the lecture. John, thanks for being here, and I'll hand things over to you.
Well, thank you very much. I want to start by recognizing Dr. Dennis Mertz of the University of Delaware, who was originally slated to give this lecture, but health concerns have forced him to withdraw from this, but he, in fact, did get the first draft of the presentation together, and I think he deserves a recognition for having done that. So let's get started. As Brent mentioned, this is the fourth of a series of lectures, but because of these health concerns, it's been delayed until now. And this deals with loads and analysis. Obviously, when you're designing a bridge, this is an extremely important part of the whole process, so let's get on with it. The lesson agenda includes some introductory material, loads, permanent loads, transient loads, limit state load combinations, and the LRFD specification is written around 4 limit states, things that happen at strength, near the usable total capacity of the structure, or at least the components of the structure, things that happen at service, routine loads that you would expect to find almost every day, extreme events. These are loads which occur so seldom that they couldn't be called strength. And in fact, what we're talking about here is vessel collision, earthquake, vehicle collision, and other loads which might have a return frequency in the hundreds of years. So we gave them their own special category, extreme events. And fatigue and fracture, something very important to consider in steel bridges. Then the analysis area, we're going to look at some of the approximate methods that are used in most bridge designs and the movement towards the use of more refined methods of analysis. I want to start with some introductory concepts. One is design life. Now, design life is a period of time on which a statistical derivation of the transient loads is based. In these specifications, 75 years was established for this, and as a practical matter, because the extreme event loads are such long return period loads, it turns out that this is basically the live load that we're dealing with here and perhaps the wind loads. Now, the fact that we say the LRFD specification provides a 75-year design life does not mean that it's a guarantee that the structure will serve the 75 years. It's assumed that the bridge will be maintained. We're still not in a position where we're going to design them, build them, and leave them. So if you expect to get the 75 years, As an owner, you have to honor your part of the bargain, which is to maintain the bridge. The other concept is service life. This is a period of time that the bridge is actually expected to remain in operation. This might be considerably longer than the 75 years, or it might be shorter. Sometimes for reasons dealing with geometrics and traffic changes, bridges get replaced a lot sooner than 75 years. We have other bridges that have been in service for well over 100 years. So service life and design life are two separate concepts, and it's important to keep them straight in your mind. Now, these limit states. The service limit state refers to stresses, deformations, cracking under regular operating conditions. Strength limit states refer to the strength and stability during the design life, during the 75 years that the loads are established for. Extreme event, as I said a few moments ago, relates to earthquakes, ice, vehicle and vessel collision, and other things with extreme recurrence intervals. And fatigue and fracture was covered in Section 8 of these lectures, so I don't think we need to cover that again, except to show you how that fits into the design process. All right, highway bridges designed in the United States and several other foreign countries are typically designed for the forces and requirements specified in the AASHTO LRFD bridge design specifications. Broadly speaking, this is the third generation of bridge design philosophy embedded in the AASHTO specifications. The first was allowable stress design starting in 1931, and then in the early 1970s, load factor design was introduced for certain components, and then in 1993, LRFD specification was accepted as an alternative to all this. It is now the de facto standard. There are several sections that work together to establish the philosophy and to carry that philosophy through to design methodology. They are Section 1, the introduction to the specifications where the limit states are defined in more detail, and the LRFD limit state function is established. And we will be talking about that at some length in a little while. Section 3 is loads and load factors. It specifies the loads, the factors that apply to the loads for various combinations, and the design combinations of loads that are used. It is seldom necessary to design a bridge for all the loads specified in the specification acting simultaneously. So we have combinations of subsets of those loads which, based on decades of experience, have been shown to be a logical way to proceed with the design. And then Section 4 is the structural analysis and evaluation, which lists the acceptable methods for analyzing a bridge and provides some guidance in using them. Now, the basic equation established in Section 1 is sometimes just simply called the LRFD equation, and it's written for load and resistance factor design with a series of characters in it. The first one is this eta. The eta factor was something that was very important to the bridge engineers, the state bridge engineers, when this specification was written. And its purpose was to find a home to eventually establish quantitative relationships for importance, redundancy, and ductility. I said the specification was adopted in 1993. It's now quite a few years since then, and we still don't have good quantitative information on this. Numbers were put in the specification as logical size placeholders, but there's still much research going on in trying to quantify importance, redundancy, and ductility. Gamma I is a load factor, and the factor I, the sub I applies to a load Q sub I. So each load has a load factor, and this has to be less than or equal to a resistance factor times the nominal resistance, and we call this product the factored resistance. So everything in the specification is written around these equations in some way, shape, or form. Now, I believe this was discussed at some length in Section 1, but I just want to go over again how we establish this equation with these factors in it, what we're trying to do with it. What we have here is two distributions, a distribution in Q, which is loads, and a distribution of R, which is resistance. Now, we like to think that the resistance is always greater than the loads, but in the real world, there is always the possibility that there'll be some combination of events that makes the loads greater than the resistance. This is not a happy outcome, and we try to make this as small as possible. We can't make it zero, because in a statistical world, a probabilistic world, there's always a chance that something untoward can happen. Also, if we keep making this smaller and smaller, the bridges get more and more expensive, so we have another problem with trying to make this imperceptibly small. So we have to select a target range in here that is societally acceptable and produces a reasonably economical result. We do that by separating the mean value of loads and resistance and their nominal values using those two factors, gamma and phi. And using these, we can push these two distributions apart till this gets as small as we want it. So that's what we're about here. We're trying to make this consistent and relatively small. Now, just to get a little more historical perspective on this, because these names are going to come up periodically, these are the standard loads that were used since 1944 in the standard specifications. There was a truck that was supposed to be reminiscent, at least, of a tractor semi-trailer. To make it simpler to use, the dual tandem axles were replaced by single axles. So you have this vehicle, or this load called the lane load, which is a uniformly distributed load over an area that contributes to the force effect you're trying to find, and a concentrated load. They are not used together. It's either or. This is typically for shorter spans. This is typically for longer spans. For simply supported structures at approximately 140 feet and greater, this load started to control. Now, in the LRFD specification, we have a different load. It's called HL93, Highway Load 93 for the year the specification was adopted, and it's a notional live load model, which means it isn't any particular vehicle or vehicles, but rather something intended to envelope a great deal of information. And again, this was projected for a 75-year design life. This is what makes up the HL93 load. It is an envelope loading for a worst case of exclusion loads, and I'll explain that in a minute. And if a bridge is rated satisfactorily for this load, has the capacity for this load, it will rate satisfactorily for all the exclusion loads. This is a pretty considerable load by historic U.S. practice. There are certainly other specifications in the world that have larger loads. So what we have is the HS-20 truck, now called the HL-93 truck, but basically the same geometry that the HS-20 truck had, plus the uniform load, the distributed load, part of the lane load. And these two are applied together. Or a tandem load, called the HL-93 tandem, 50 kips on two axles, 25 kips on each axle, also placed on the lane load. So it's not an either-or in the LRFD specification. It is, well, it's either-or to the extent of this or this, whichever controls. But the axle string is always applied with the uniform load, with a couple exceptions, which are pretty clearly pointed out. All right, we're going to talk a little bit about where this came from. When we started on the LRFD specification, the Transportation Research Board had conducted one of several studies that's done over time, including one underway right now, on truck size and weight across the country. And from that report, we found a number of vehicles which were exclusions, hence the word exclusion load, excluded from the various state weight laws. So you might have a law that said maximum of so many kips on a single axle, so many on a tandem, not to exceed a total, except for a given configuration. So we got these configurations on that basis. They were massaged a little bit to make them a little more general. And as you can see, they go from single-body trucks to the tandem type special hauling vehicle, to the 3S2, to very large, long combination vehicles. The largest of these weighed 140,000 pounds, and the largest of the Tridem was over 90,000 pounds. So these were very considerable loads that were allowed to run with no control whatsoever in various states. Not every one of them was allowed in any particular state, but if you looked at the country as a whole, these loads could be running with no control whatsoever. So the question before us was, does the HS-2044 live load represent this type of traffic? So we looked at what we called a moment ratio of the envelope of all of these vehicles divided by the HS-20 load, whether it was the lane load or the truck load. And we did this for a positive moment at a 4/10 point of a two-span unit, negative moment at the 4/10 point, the moment at the support, and the moment in the center of a simply supported span. And this is a match down here, 1.0. And anytime these dots are above that, those vehicles were producing considerably more load than the design load. This was a bit of a problem that we felt had to be addressed. Well, how does the HL93 compare to that same family of loads? Well, this is the same type of a graph, except now the denominator in the ratio is the maximum of the HL93 loads, either the truck in the lane, or the truck and the distributed load, or the tandem and the distributed load. You can see that these are pretty close to 1.0. We accepted about a 10% deviation on this, and the same rough comparison is available for all the characteristics we looked at. And in fact, it was the same for shear. In fact, the curves were more closely aligned, still around 1.0 for shear. Well, this is important because it suggests that if we keep working with this, we will eventually have a load factor which is load independent, because this is close to 1. And that was pretty important. This HL93 is a significantly larger load in most cases than the HS-20. This is a plot of the HS-20 truck load and the HL93 load for a 100-foot span. And this is various points along the span horizontally, this being the center line. And the vertical is the moment in kip feet. And you can see that near the midspan, there's approximately 34% more moment from the HL93 load. Now, this was without factors or anything else, but this is just the gross load. And if this were a 140-foot span, this would be over a 40% difference in here. So this starts out being a pretty significant load. Well, generally speaking, we've known all along that the HS-20 truck was a little light, but that the distribution factors in the standard specification were very conservative. A distribution factor is a quasi-analysis. It's a way of assigning the amount of load that each of the longitudinal members in a multi-girder bridge carry. In the standard specification, it was the spacing of the girders divided by a constant, usually 5.5 in most practical cases. Well, it was known that this could be very conservative. So there have been many efforts over the years to develop improved ways of doing this. So what we have here is a distribution factor which was developed in an NCHRP project done by Roy Empson and his company. And you can see that this is a lot more complicated than S over 5.5. It's a constant plus the spacing divided by another constant raised to an interesting exponent, 0.6. The spacing divided by the length raised to the 0.2. And then this interesting collection of terms right here raised to the 0.1. This collection of terms deals with the stiffness of the girder divided by the stiffness of the slab. It's the ratio of the longitudinal to the transverse rigidity of the bridge. Now, if you go back in the literature, we would find that sometime in the late 1940s, early 1950s, when Nathan Newmark was doing the studies which eventually led to S over 5.5, he had proposed an improved equation that had a parameter called H in it, and H was the ratio of the longitudinal to the transverse rigidity of the bridge. So what we're doing here is collecting things that have been known for quite some time. Now, this is a plot that shows in metric units, unfortunately, what happens comparing the S over 5.5, which is this, the bold curve, to the results of this equation. And you can see that in some cases, there's almost a 50% difference between the distribution factor from S over 5.5 and what's given by this equation. However, much to our surprise, there are cases where for particular geometries that were used more in the past, actually, the S over 5.5 could be unconservative. This was quite a surprise. We've all grown up to believe that equation was always conservative, but that was not necessarily the case. So what we're doing here is taking apart two compensating characteristics of the standard specification, the load and the distribution factor. And that's important because as we go forward, we want to be able to make adjustments to all these things in a logical way. So by taking the time to go back and sort these things out, we are able now to go forward in a very logical, consistent way. In the LRFD specification, the measure of safety is not a factor of safety. It is a reliability index, which is a much more robust way of looking at this. And if we look at the reliability index provided by the standard specifications for a variety of cases. Now, span length is horizontal here, and the data in each of these represents spacing and material, steel, reinforced, and pre-stressed concrete. And the spread of information in the old spec is given by the narrow red line. And these close clusters here are what we get for the same geometry bridges using the LRFD specification. The objective was uniform safety as indicated by the statistical quantity reliability index. And that was achieved by these various things which we have talked about so far. So to put it together, what we want to do is remember that we're talking about a new live load, new distribution factors, calibrated load factors and resistance factors to achieve the result of very close clustered reliability indexes. Now, one of the things about using the reliability theory is it's a comparative standard. So one of the things we look at when we try to figure out approximately where we want to be is what has worked in the past. And this number, 3.5, turns out to be pretty close to the center of the current population which has served us well. And that is a number which several other countries have landed on as a reasonably safe, economical way to proceed with a component design. But what we want to do is take this characteristic and shrink it down to that. Okay, so let's go on to what we might expect to find here as we proceed with this. When you actually get to do some designs with the LRFD specification, you should see the following general trends. Many of the designs, by the time you actually get them done, will be similar, but some won't, because when we try to tuck in the extremes, there are some designs somewhere that are going to change. Sometimes you'll find the total weight of material is the same, but it's distributed differently along the bridge than it used to be. If the distribution factor is one of the improved factors, for example, a multi-girder bridge, then the reduction in that distribution factor will mute the effect of the heavier HL93 load. It won't eliminate it completely, but the two of those will work together to offset each other a bit. On the other hand, if you're designing something for which there was no improvement in the distribution factor, and a fair number of types of structures, there was no change, then you will find the HL93 in all its glory as a considerably heavier load. You will find that the exterior beams often carry more live load than the interior beams. This is consistent with any number of bridge instrumentation studies. It was not clear in the past specification that was the case, but you'll usually find that happens here. You'll also find that shear has a proportionally bigger change than moment. And again, I'm going to stress this, that if the distribution factor is unchanged, then the HL93 will have a significant impact on your design. And just to make it very clear what we're talking about here, we're talking about a notional load, not a specific vehicle, meant to envelope a series of events, and it is the tandem on top of the uniform load, the truck on top of the uniform load, and in the case of negative moment at a pier and interior reactions, it's two trucks 50 feet apart with the uniform load placed where it should be for maximum effect times 0.9. Okay. Now, of course, when you design, it's more than just the vehicle. There are other things that work together to make the total live load demand. And they are the load factor. We've looked at that. Load distribution or analysis. We've had a quick look at that. Multiple presence and dynamic load allowance, or what used to be called impact. So let's take a look at a few more of these characteristics. Multiple presence deals with the probability that several lanes would be loaded by very similar vehicles, we call them fully correlated vehicles, simultaneously. The multiple presence factors of the LRFD, the multiple presence factors are given in this article, and a lot of these slides will tell you exactly where to find what we're talking about. So when one lane is loaded, the multiple presence factor is 1.2, two lanes 100%, and as you increase the number of load lanes, the number decreases. Now, in the standard specification, the values were 1, 1, 0.9, and 0.75. So I want to take a minute to explain why this one is greater than 1. The database we had available to project the live load with had a limited number of trucks, 10,000 trucks that were thought to be heavy trucks and that were stocked and weighed in Canada. They were very similar trucks to the type that run in the United States. But when you're talking about 75 years and a road that has an 80 TT of, say, 5,000, you could be talking of tens of millions of repetitions. So in order to project that far into the future, with the limited amount of information we had, as you got further and further out in time, the projection got more and more questionable. So we decided to go with 2 lanes loaded and a shorter time period and make that the base case and scale everything around that. And then to consider not just the increase in growth of the loads to 75 years, growth in the statistical projection, not growth as in legal load. We put all the uncertainty on the least likely event and put that in at 1.0 or 1.2. So we tried to make the most use we could with the available information. The dynamic load allowance is what used to be called impact. Now, impact is sort of a jolt, whereas dynamic load allowance might have a jolt hitting an expansion dam, hitting a pothole, but also a dynamic event, a sprung mass on a flexible structure. So in order to take that into account, and since these results were based somewhat on that type of a study, tuned mass, a sprung mass on a span, we have several changes in terminology and values. Joints, we are using 75% impact from. When we did this was largely taken from instrumentation on the A4 near Paris. Since that time, a number of other studies have been done here and elsewhere that confirm that that's not a bad number to use for something which gets struck by the wheel directly. For all of the components, for fatigue and fracture, 15%, and for the strength and service limit states, 33%. Why is this different? Well, particularly for the strength limit state, we're looking for the once in 75-year event, whereas fatigue is made up of many repetitions of a more routine loading. And for that case, 15% has been shown to be a pretty good value. Okay. So this dynamic load allowance is applied in the following way. It's applied to the wheels, the axles. So it's applied to the truck or the tandem part of the HL93 load, but not the lane load. Why not? It's generally been found that as more trucks are on a bridge simultaneously, as represented by the lane load part of the HL93, that the dynamic effect decreases because they cancel each other out. It's not applicable to walls or superstructure reactions, walls that do not carry superstructure reactions, and it's not applicable to foundations, which are completely below ground. The fatigue loading is a little bit different. This is basically what is traditionally known as a fatigue truck, and it's similar to the HS-20 truck, except it's spaced 30 feet between these axles. And this is one that, if you've designed bridges before, you would be very familiar with. It's used in one lane in the LRFD specification without the multiple presence factor. Again, because this is a repetitive load situation. Given this loading and the stresses it produces, you check susceptible fatigue details. You had a lecture on fatigue, so that should be well covered by now. The rating process, and we're going to talk about rating closer to the end of the lecture, that process is also consistent with the design process now. So all of that's been pretty well tied together. Now, considering the various loads that you would design a bridge for, we have loads which are called permanent loads and loads that are called transient loads. And this distinction is made for the purpose of assigning various factors. The permanent loads are always present and are factored by either a maximum or a minimum load factor, depending on what you're designing for. And we're going to go over that in some detail in a few minutes. The transient loads are present and multiplied by a maximum load factor, or they are not applied. They are either there or not there. So let's look at some of these loads. And this is quite a cast of characters here in terms of the various things that you have to consider when you're designing a bridge. So there are various types of dead loads. And again, I point out that the article numbers in the specification are often here with the titles. So there's a dead load of component and non-structural attachments. There's a dead weight of the wearing surface and utilities, and that is a little bit higher than some of the other dead load factors because wearing surfaces are generally less consistent than the factory-type components. There's vertical earth pressure from fill. There are other types of earth loads. There's horizontal pressure, surcharge loads, and down drag loads. We're going to look at some of those as we go along. So here's a horizontal earth pressure load. And you'll find that there are a lot of these drawings with pressure distributions in the specification for various types of walls and various types of conditions. This is just your basic load behind an abutment. This would be the horizontal load located H/3 from the base of the element. It's the same triangular distribution that's been used for decades. So the pressure is a coefficient, a constant for any given case, times the density of the soil times the depth, Z, from the top. Now this pressure coefficient depends on how you see the wall responding. And it can be one of three things, K0 or K0, K active, and Kp. K0 is used when the wall is not perceived as moving. K active is used when the wall is perceived as moving away from the soil, being pushed away by the soil. And Kp is passive. That's the case where the wall is actually tilting back into the soil. Obviously, Kp is usually much larger than Ka. And gamma S is the unit weight of the soil. So in the cases where these distributions are given, There'll be an equation or a relatively simple geometric case for you to calculate the shear and moment. This is applied for permanent walls, temporary walls, whether they're discrete or continuous types of walls, anchored walls with either multiple or single levels of anchors, mechanically stabilized earth walls of various types, and prefabricated modular walls. So there's a great deal of information in the specification for dealing with these loads. There's also a surcharge load. This is a load which is on the soil above or behind the footing. So it's usually some sort of a coefficient times a load intensity. And there'll be various graphs and calculation models for various types of pressure distributions. So for a uniformly loaded strip, for example, there is a distribution assumed on the wall. There's an equation for that. And with that equation, you can figure out what that distribution intensity looks like and calculate shear and moment at various places from it. For a point load, the situation gets a little more complex because of the geometry involved, but there's an equation for that to help you. And there's really quite a series of these. Now, one of the other soil-related loads is called down drag. We're all familiar with the idea that, for example, a drill shaft or certain types of piles resist their load through a combination of friction along the sides and a bearing under the element. Well, Brent, can you hear me again?
John, we've got you back now.
Okay, good. Sorry, the power went out here. Okay, so if you reverse the situation now and think that the soil is settling relative to the foundation element, then you can get to the place where instead of resisting, you're driving against the pile. This is called down drag. And where it applies, this has been found to be a significant enough load that there are cases where it has actually pulled foundation elements out of footings and driven the element through a weaker strata. So we don't always have this situation to worry about, but where we do, it's important to know how to take care of it. Okay, Brent, I seem to have lost the ability to move the slides. Can you move the next one, please?
Sure. And are they updating on your end?
No, I have a network connection error, it says here.
Okay. All right. If we could, everyone, if we could just stand by for 1 minute, we'll try to get this resolved.
Okay.
Did you happen to lose your internet there, John?
I think maybe I did.
Okay.
Sorry, we had a power glitch that got the power in the entire neighborhood.
Okay, we'll get this resolved shortly. Mike, can you pull us in for 1 second, please?
Yes, sir. Ladies and gentlemen, please stand by. Please continue.
All right, thank
Okay.
you, everyone. We apologize once again for our technical difficulties. We will continue now on slide 41.
Okay, so the various transient loads, of course, include the live load, and there are several components to that. There's the vehicle load that we just looked at. There's a pedestrian load. We looked at the dynamic load allowance, but there's also a centrifugal force on a curved bridge, a braking force when traffic deaccelerates, but there's also one to some degree when it accelerates. There are truck collisions, and there's a live load surcharge behind retaining walls in some cases. There are also water loads, and that's simply WA, a water load, which is pretty well known, as you might expect. There's a wind load of two types. There's wind on the structure and wind on the live load. Now, these are quasi-static loads. They are not dynamic in the sense of structure-force interaction. There's an ice load, and as we'll see, they can be rather large, and an earthquake load. Now, the earthquake load is one of those extreme event loads, and in fact, the acceleration maps that you use for that now in the LRFD specification are 1,000-year earthquake return periods. There's also a second choice for seismic design besides what's in the LRFD specification. What's in the specification is called force-based design. There's also a displacement-based design called the Guide Specification for LRFD Seismic Design. There are various types of superimposed deformation: uniform temperature, temperature gradient, shrinkage, creep, and settlement. Now, the unique thing about superimposed deformation is they are not in equilibrium with an applied load. It's not a gravity load or a horizontal load that they are in equilibrium with. So there are some unique things that can happen to these as you approach significant damage at a strength limit state. And as you'll see, we took advantage of that. There are friction forces, on the next slide, and vessel collision forces. Where you are in navigable waterways, either the barge-type traffic or ocean-going traffic, these forces can be rather large and have resulted in very significant loss-of-life situations. Next. The transient load, again, is a live load. We've looked at that before as the HL93. We've looked at the superposition of the vehicle and the lane part or uniformly distributed load, and we've looked at multiple presence factors. Next. The other transient loads include the pedestrian load. There's one where there are sidewalks on the bridge and a separate load intensity when it's a pedestrian bridge itself. And there is, in fact, a separate guide specification for the design of pedestrian bridges available now. And we have already looked at the dynamic load allowance, IM. Next. The transient loads include the braking force. Now, the braking force is 25% of the weight of the design truck or the tandem axle load, or 5% of the truck or tandem plus the lane load. And the number of lanes in a given direction can be used to work with this. These loads are relatively large compared to the traditional loads in the standard specification, or that were in the standard specification. They are, however, relatively benign compared to the type of braking forces found in some other specifications. When we set this up originally, the 25% was set to deaccelerate a truck within the required stopping distance required by the Interstate Commerce Commission. Centrifugal force applies to bridges on a horizontal curve, and again, that's the weight of the truck or the tandem times a coefficient C, which in turn is related to the velocity of the traffic, the gravitational constant, and of course, the radius of the curve. Next. The vehicular collision force, CT, is a 400 kip force in a horizontal plane in any direction. And this is applied to substructures within 30 feet of a roadway or 50 feet from the center line of rail traffic. This is a relatively large force, although there have been some instances lately where it would appear that larger forces were generated. The 400 kips comes from work done at Texas A&M by Hirsch and Booth. This is the group that worked on the load for traffic barriers, and from that work they imputed a collision force for substructure. There's a lot of work being done on trying to sharpen the pencil on this to deal with this as a function of the probability, given geometry and other things, of the impact actually occurring. And again, CV is the vessel collision loads from ship or barge. Incidentally, this is a load which is handled in a truly probabilistic way, in that the probability of failure within a certain period of time, either 1,000 years or 10,000 years, is computed based on many characteristics of the vessel and the waterway, but you actually calculate probability of failure. Next. Ice loads caused by crushing or failure of bending of ice can be extremely large, and there are equations here for these forces. There are other types of forces besides just the impact type of force that are also possible from ice as the water fluctuates, and they are called out as well. Next. Other transient loads include friction forces caused by sliding between members, and for this we would use extreme friction coefficients, which are either specified or available in the literature. And again, there is a live load surcharge from live load within 1/2 of the wall height. We have equations for that that again deal with various coefficients that from the geotechnical community, as well as a function of the wall height. Continuing with the transient loads, water, of course, is a load we have to deal with too. It's a pressure load. It can be buoyancy. It can be a stream force. And there are equations in the specification for the longitudinal and lateral force based on drag coefficients. Now, when you think about moving water, the thing you think about first and foremost is scour loads. And so why isn't scour here? Well, scour is a changed condition, a change in foundation conditions. And you have to consider this. You have to consider whether you have aggregation or degradation, whether you've got contraction scour or local scour, and different types of scour causing different changed foundation events are used for various situations, and they are called out in the specification. Next, we have the wind loads, wind on structure, wind on live. There is a pressure distribution for this that is based on a meteorological type of analysis, and it's based on a 100-year base velocity. Now, if you're more or less than that, there's a way to adjust for that. And it's also based on what's called the boundary layer, assumed to be 10 meters high. So if you are above or below that, there are corrections you can make. Almost nobody corrects for being below this 10-meter height because that lowers the force, and that's kind of an insignificant change. But if you are significantly above that datum plane, the load increases. And the way to handle that is given in the specification, and that can be significant if you're high above land or water. There's also wind on the live load. There's wind, a uniform line load based on the size of the vehicle, and it's applied 6 feet above the roadway surface. That's a horizontal load. But there's also a vertical wind pressure up, a lift, that is used as a separate case, not present with the wind on the live load. And again, there are continuing other transient loads, the ones that I mentioned before that are by and large superimposed deformations, not in equilibrium with an applied load. And these are uniform temperature, temperature gradient, creep, shrinkage, and settlement. And there are various various characteristics of these that are called out, and an equation or calculation process for these is also given in the specifications. This is considered largely for substructure design, but it does have some influence on certain types of superstructures. Now, there are load and load factors for each limit state written in load combination form. These are applicable for each of the load combinations, which we're going to see in a minute. There are load factors for the permanent and transient loads and load modifiers, as we saw before, for ductility, redundancy, and importance. So the load combinations, where the average designer spends a fair bit of his design effort, is given in Section 3 in the load combination table 341-1 and its supplementary table 341-2, and there is now yet another one. So what happens in this table is we find out exactly how to deal with the LRFD equation, which is shown on the bottom of that slide. So if we go to the next slide, we're going to spend a little time on this table because, again, this is the basis of design. You remember I said earlier that AASHTO very seldom requires that you design for all the loads simultaneously because of the high improbability of that occurring. And I can't tell you when the load combination table first appeared in AASHTO specification, but I can tell you it's some form or another of this idea has been in the specification for as long as I've known anything about it. In the standard specification, because it treats both load factor design and allowable stress design, there are two of these tables. And after you've decided which design philosophy you're going to use, you use one table or the other. In the LRFD specification, there is one table. This is that table. And this table, going down the extreme left column, links all of the limit states. So there are combinations that apply to the strength limit states, combinations that apply to extreme event, combinations that apply to service, and combinations that apply to fatigue and fracture. All right, so given that, we have all of our limit states and the various individual ways we should look at them in that first column. Across the top are all the loads that we just looked at. Notice as we do this that the earthquake, blast load, BL, ice, and the various collision loads are under a heading that says use one of these at a time. So you don't have to deal with several of these. There's a lot of research going on now trying to look at multi-hazards, but for the current time, we don't deal with more than one of these at a time. So these various loads, combinations, are used for particular parts of the design. So the strength 1 case is the basic load combination that relates to the normal traffic usage without a significant wind. Strength 2 relates to the use of the bridge by an owner-supplied vehicle other than the HL93. A lot of owners require the design for a state-specific truck, and that would be used in this particular load combination. Load combination strength 3 deals with a maximum wind case. Now, to start with, that wind is about 100 miles an hour. It could be a little less in the middle of the country, and certainly a fair bit more along the coast where we're subject to hurricane loads. But that's a maximum wind case. There's no live load for this because we expect that the wind is going to be strong enough that vehicles are going to have a lot of trouble being controlled and will not be driving at that time. Strength 4 is a special case, in fact a deterministic case, used for structures that have very high dead load, where the live load is almost insignificant. And this is usually a span of over 600 feet. That's just a way to look at it. And what this is guarding against is that because the load factor on dead load is quite low, the reliability index could be low for that case. So we put a floor on how low we would go on this, and that's the strength 4 case. The strength 5 deals with vehicles and moderate wind. Extreme 1 is an earthquake case, and there is a characteristic there, a load factor called gamma earthquake. This is not well established with any kind of consistency and uniformity of thought. So there is some commentary that gives you guidance on how to choose this. Typically, the owner will have chosen this. Extreme Event 2 deals with ice loads, collision by vessels, check floods, certain hydraulic events with a reduced live load. Because after all, the normal live load is relatively smaller than the once in a 75-year event that the HL93 is supposed to handle. Service 1 is comparable to Strength 1. It's normal use of the bridge in a moderate wind, and it deals with things like deflection control of certain types of structures, crack control, and that type of thing. Service 2 is what used to be called the overload case, and this is a moderately larger load, not as large as the Strength 1 case, but it's for control of yielding, premature yielding in steel structures and control of subcritical details. Service 3 deals with a longitudinal analysis of pre-stressed concrete structures with the objective of providing crack control. Service 4 is for tension from the bottom of pre-stressed beams. And Fatigue 1 is infinite life fatigue. I believe that was covered in the 8th lecture. And Fatigue 2 is finite life. Now you'll see in the table that I've made a correction to the load factor on the live load for Fatigue 1 and Fatigue 2. This is the information that was passed last June at the AASHTO meeting in Minneapolis. So you're absolutely up to date here. So now let's just take a look at how we're going to employ the equation with the summation sign using this table. Well, we're going to put down the load factor for each of these loads, DC, DD, and so on, down the permanent loads. So we've got to find this gamma P, and we'll find that in a moment. But each of these loads gets multiplied by a load factor and then added to a running total of all of them. And then if we're doing Strength 1, we go pick up the live load characteristics, multiply them individually by their load factor, add that to the running total, deal the same thing with water, friction, and so on. So it's just a sum of products until we get the force that we want here. Now let's take a look at the next table. Okay, now this table shows load factors for permanent loads, and you'll see that there's a maximum and a minimum. The LRFD specification deals with extremes. An extreme can be a maximum or a minimum. And if in the real world loads can be heavy, they can also be light. And we need to take that into account where it may be important. So there are different factors for these various loads that are used when we're looking for the maximum event, other factors when we're looking for the minimum event. Well, why do we care? Well, there are some cases where, for example, the permanent loads add to the stability of the structure. So we want to at least take into account the possibility that they could be light, and therefore the structure might be less stable. Now, nothing says that you have to look at cases that just defy logic. I mean, if you can look at this table and say, well, clearly I only want the maximums, then just do that. For example, if you are looking at a simply supported structure, let's just say for fun, a right square bridge, and we've got the loads in one girder, and we were designing the girder. Well, it should be intuitively obvious that having all the maximums create the worst event. So we just wouldn't make the calculation with the minimum. On the other hand, if we're designing a foundation, if we're looking at bearing capacity, we probably want all the maximums. But we also have provisions for maximum eccentricity in a footing. In that case, we might want to discount, use the minimum factor, on those loads which decrease the eccentricity, which would usually be the vertical dead load. All right? Now, there's a lot of commentary about this in the specification because we don't want people making numbers that just plain don't make sense or just defy logic. So read that carefully, and it will provide you a lot of guidance in how to use these two factors. Okay, so on the next slide, we just sum this up by saying that what we want to do here is produce the maximum or minimum total effect as appropriate, and that loads that reduce the forces being considered should be factored by the minimum factor. And again, these are the permanent loads. The transient loads are either there or not there. Let's take a look at analysis. We've seen that there are some approximate equations that can be used, the distribution factor we looked at earlier, but there's also the possibility of doing a refined analysis. That usually means grid or finite element analysis. For the approximate methods, for the most part, consist of these load factors produced by Roy Empson, and there are several pages of those in the specification for various types of structures and conditions. The refined methods in practice are usually grid or plate with eccentric beams for slab-on girder bridges. And of course, finite element methods are also possible in the sense of continuum finite element analysis, but the bulk of the practical work is still done with grid. So why do we want to do this refined analysis? First of all, in some cases, the specification just plain requires it. Areas of heavy skew, sharp curvature, and large variations in stiffness are keys for finding areas where the simple methods don't apply. Those methods were developed for a common range of variables. And if you're outside those variables, and by the way, those variables are given in the specification, then you have to do something more. And that's a refined methods of analysis. There's also the possibility that significant savings could be realized because there still is some conservatism even in the new distribution factors that we're using. Next slide. Additionally, the refined methods provide a better understanding of the behavior of the structure. It's easier to identify load paths, particularly as the geometry of the structure gets more complicated. And it's becoming easier to do this all the time. The software tools are just getting better and better. And very importantly, sometimes when you're dealing with an existing structure, you can take advantage of the extra capacity resulting from the better distribution of load in the structure. And this may be an alternative to weight posting a bridge, to repairing it, or replacing it. So when you can leverage an existing structure, then these refined methods become even more powerful. But it needs to be done correctly. In the next slide. Sometimes it's harder to find the error in these methods. The complexity can obscure behavior as well as enable you to see the behavior depending on the situation. So there's a need for some sort of guidance and benchmarks. Information is currently scattered around a lot of places, and it's not necessarily bridge focused. Next. So with this information in mind, the FHWA determined that a manual was needed to improve the consistency of application and to make the use of refined methods analysis easier to employ. So they have an IDIQ contract with Lehigh University, and as part of that team, Majeski and Masters is writing a manual on how to do this work. Next. The manual is being developed under two tasks. The first task is complete. A draft manual is available on the FHW website. There's a link to that. I'll give you just a second to copy that down while I tell you that the second part of the work, task 2, is currently well underway. Okay. Next, in terms of writing this manual, the objectives and approach of this was to try to provide greater consistency in the application of FEA to bridge structures. There's considerable latitude in what could be done here, and it's been found that in some cases people are getting interesting results. Let's just put it that way. So the FHWA was interested in finding a consistent, well-advised way to do this. So what we're trying to do here is raise the level of basic understanding to encourage wider application of this, to avoid blunders, understand behavior, and introduce economies into design. Next. So the approach to the manual is to keep it very flexible, to encourage initiative and creativity, to avoid deep mathematics. Finite element analysis can get pretty far into the weeds of mathematics, and we've tried to avoid that totally. We're concentrating on application, and have tried to avoid software specifics to the extent possible. We're trying to keep this generic. We're not interested in promoting any particular software, rather increasing the understanding of how to do this. Next. So in terms of general topics, the first task focuses on the most common bridge types. There is a minimal amount of material-specific information, just enough to get that job done without, again, getting too far into the weeds. It's based on linear elastic behavior, and it's based on static analysis. Task 2 will provide material-specific topics, nonlinear behavior, dynamic behavior, and a few other things. So if we look at the next slide, Task 1 has a forward where we try to explain where some of these methods came from. There's a definition of the refined methods of analysis. Modeling in Section 3, very important. Verification of your model in Section 4. Section 5 deals with load application. And 6 is analysis to design. How you take the results of your refined analysis and relate that to the types of things that the design specification expects to see, which is usually thrust, moment, and shear. And then in Section 7, there are a series of very detailed examples. Next. So the introductory chapter addresses the purpose and goal of the manual and provides background on the development of FEA. And then there's a series of definitions for 1, 2, and 3D analysis. But that would seem terribly clear, but when you get into this, it really isn't, because of the possibility of having a curved 1D analysis. And because of that, we had to be very careful about how we're defining these things. Next. In terms of more of the basics, the grillage analysis has a lot of in-depth detail on the method called plate with eccentric beam. And then the grillage, or grid in astro terminology, is still popular with some software and is a refined method when compared to the 1D. And the advantages and disadvantages of these, as well as the full-blown 3D FEA, are called out in this manual. We also, on the next slide, have spine beam modeling accounted for, which is usually used with concrete structures, but could be applicable to single or multi-cell box structures. Next. So we also have a section on the use of the finite element method with strut and tie modeling. Strut and tie modeling addresses disturbed regions in concrete bridges where the Bernoulli beam theory doesn't apply. And one way to build one of these models is to do an FEA, understand how forces are trying to get from one place to another in the structure, and then simulate that with struts and ties. There's also a principal stress check available with that. On the next slide, there are examples that compare the results of 1, 2, and 3D analysis. And these examples are pretty carefully detailed in terms of sample calculations for just about everything you need to do. And it shows that, surprise, surprise, the 2 and 3D methods do have definite advantages over the 1D methods. The steel examples include steel girders, which are straight and square, and steel girder bridges, which are curved and skewed. And there are some concrete examples also. On the next slide, this is perhaps the most complex of the bridges in the first volume. This is a curved, skewed, multi-girder bridge of the geometry shown here. And again, after it's explained how to build the various models for this bridge, the results are compared 2 and 3D. For this particular structure, the 1D methods really don't apply, right? So the 2 and 3D methods are compared in terms of moment plots, and on the next slide, deflection plots. And any differences in these are pretty well explained. In Task 2, which is in progress, we're dealing with other types of bridges, soil structure foundation interaction, connections, nonlinear modeling, stability analysis, dynamic analysis, and more examples. We're getting pretty close to the end here in the time, but because we lost power here, I'd like to take a couple minutes more, if that's okay, Brent, and talk about other loads.
John, yeah, go right ahead. We're doing fine.
Okay, good. All right, so on the next slide, I introduced the idea that there are other loads for other purposes than design in the AASHTO documents. And this is typically used by most engineers for ratings, which is a capacity requirement of the bridge inspection, the NBI, National Bridge Inspection Program, and postings, which is an issue of signage. So these are used for administrative issues and signage issues. They deal with routine commercial traffic, and there are truck and lane load models for this, as well as state legal loads. There are specialized hauling vehicles, I'll show you some pictures of those, which are multi-axle, single-unit trucks, and there's a notional rating load and 4 single-unit configurations. So let's take a look at how this works. On the next slide, we talk about rating and posting of bridges. There's a separate document for this other than design spec, and it's called the Manual for Bridge Evaluation, or just MBE. Ratings are a usable capacity of a given set of loads to 2 operational criteria called inventory, which is routine everyday usage, and operating, which is occasional usage by heavier vehicles. And again, I'll just say that the postings are weight limit signs. We've all seen the 10-ton sign somewhere or something like that, and these are largely policy decisions. This is a more complex issue for most owners than simply the ratings. The MBE allows a choice of 3 ways to do this: load and resistance factor design, allowable stress design rating, or load factor rating. So it's LRFR, ASR, or LFR. The loadings vary with the method and the purpose for which the bridges are being rated or posted. So there are a lot of choices here. Read carefully. But it usually involves some combination of the state legal loads, the HS loads, or the HL93, and the vehicles I'm about to show you. Next. One set of vehicles deals with what's called routine commercial traffic. And if you took the time to compare these to the HL93, you would find that these are considerably less demanding than the HL93 on first blush. Now, there are various factors that go with these, but these are thought to be vehicles which are legal just about everywhere. And then there's routine commercial traffic for longer span bridges, in the next slide, which would be structures over 200 feet. And if you go one more, you'll see an axle string, which turns out to be the 3S2 from the commercial vehicle, on top of another uniform load, which is only 2 kips per linear foot. And on the next slide, a 2-vehicle combination used for negative moments and reactions at interiors. Okay. Continuing, one of the recent issues that's come up is the so-called special hauling vehicles, or SHVs. These are trucks which comply with Formula B, which I'll show you in a minute, and therefore meet all federal weight regulations. They have high axle loads concentrated over a short distance, and some of them have movable axles which can be raised or lowered as dictated by the amount of weight that they carry. So on the next slide, we have the federal weight limit, the federal bridge formula. And there are single axle limits, tandem, gross weight, and then the bridge formula for total weight. Now, this is the total weight allowed on a string of axles of some distance, as given by this formula. And this can be any set of consecutive axles within the vehicles. This formula has been around for a little while. And, next slide, the trucking manufacturers have found ways to optimize what they can do with this formula. And what was found recently is that they have produced some of these vehicles which are considerably more demanding than originally thought when the federal bridge formula was established. So because of that, there's been considerably more work done recently on how to address this. And on the next slide, we have the notional rating load, or NRL. Now, this is basically a scanning load. It's meant to envelope a lot of these special hauling vehicles. And if your bridge rates for this, you don't have to look any further in terms of the special hauling vehicles. If it doesn't rate for this, seems to not have enough capacity, then you can sharpen the pencil by looking at 5 other configurations shown on the next slide. And these are the posting vehicles for the Federal Bridge Formula compliant special hauling vehicles. Why would you bother if you've already looked at it for the notional rating load? Well, again, the reason is because the notional rating load is an envelope and therefore is apt to be heavy for some bridges. So by going to this set of 5, you might be able to squeeze a little more capacity out of the bridge and not have to post it so much. So in the next slide, we have the general rating process for these state special hauling vehicles. You need to be somewhat cognizant of the vehicles operating in your state in case there are some exceptions. There may be state-specific rules that could be a little bit different than the general MVE rules. And again, this single notional rating load is a screening load for many of the special hauling vehicle configurations, and there are, it says 5, there are 4, I'm sorry, I said 5 earlier, 4 configurations that can improve the posting to some degree. So this deals now not only with the design of the structure using the HL93 and the LRFD specification, but the administration of the system through the use of the MBE, the commercial loadings, and the Federal Bridge Formula compliant special hauling vehicles. And with that, and with great apologies for the power outage, we'll turn this over to questions. And Brent, as you might gather, I can't see the questions, so if you would read them, I'd appreciate it.
You bet. Thank you, Dr. Kalicki. We do have several questions that have come in. We'll do our best to answer as many as we can with the time left. I'm going to go to slide 16 for our first question.
Okay, that's the one with the HS20?
Correct. And the first question was, can you just clarify, did you say that the truck controls for shorter spans while lane loads control for longer spans?
Well, let me expand on that a little bit. Okay, there is also another load that's in this family that's sometimes used, I think, just for interstates. It's called the alternate military load, and it was 2 24-kip axles. So if on a really short span, those tandem loads might control. Generally speaking, from about 30 or 40 feet up to about 140, you would expect the truck to control on a simple structure. For 140 feet and more on a simple span structure, the lane load almost always controls. If the structure is continuous, all bets are off. All right? The AISC has some tables that can help you discern what controls where, but by and large, if it's a continuous structure, especially a variable span continuous structure, you're probably going to be looking at the whole set. Can I expand on this just a bit more, Brent?
Sure.
Okay. Now this is called the HS20 S1644. 44 again being the year it was adopted. However, within a handful of years after this, and certainly by the late 60s or early 70s, there were some states already designing for HS25 because they knew that these big vehicles were out there. HS25 does not have the same semi-horizontal relationship to the exclusion loads that the HL93 does, but it was a step in the right direction. So the idea of increasing the design load has been around for a long time. Okay?
Okay. Now I'm going to move ahead to slide 18.
18. Okay, that's the HL93 design load model.
Correct. And so this is a question in regards to the rear axle spacing. At what bridge span lengths does the rear axle spacing change from 14 feet to 30 feet for the design truck when doing designer analysis?
Okay. Now, intuitively, you would expect that the shorter span would control off to 14 feet rather than 30 because you're concentrating the load over a smaller distance. And that logic generally applies. But when you're talking about a continuous span, let's say a 2-span continuous unit, and we're looking at negative moment, the possibility of dropping those two 32-kip axles at significant points of the influence line, the negative moment becomes important. You might actually hit the golden spots by increasing this to 30 feet. So it depends on the type of structure you're involved with and what you're looking for. Does that answer that?
Yes. Yep. Thank you very much. All right. We're going to move ahead to slide 30 now.
30.
This looks at the dynamic load allowance, IM.
Yes. Okay.
Okay.
Got it.
So the question is, the dynamic load allowance, IM, for deck joists indicates 75%. Does that apply to steel joist member design or the joist connections only, or does it apply to both?
Okay, I hope it says deck joints, expansion joints.
It does. I apologize. The question is written as joist. I think they meant joints. I apologize. So the question is, does it apply to joints, the connections, or both?
Well, I think that I suspect we don't say that so specifically, but it seems to me that what we're protecting against here is the impact on an expansion joint, you darn well better design the connection to the concrete deck for that load too. I mean, that's where it's going.
Yeah. Okay. Okay, slide 31 then, the next slide.
Yes. Got it?
Give me 1 second here, I apologize. The question is, are bridge abutments considered completely underground and thus should not be subjected to impact loads?
Now, it's my understanding that this refers to the foundation, the footing, right? Not necessarily columns or walls. Now, if you have a retaining wall with no superstructure reaction on it, then there's no impact. But if you have an abutment wall, I think you should be designing that for the impact until it gets down to below ground.
Okay. All right, the next question is related to, I'm slide 47, the braking force. Can you clarify, is the braking force a horizontal load?
I believe it is almost always treated as a horizontal load, but I could see where someone might think that since that force is probably originating, the center of mass has to be a factor too. And I think what I'm interpreting the question to be is, does that produce an up and down reaction on the front and rear axles, for example? And I don't believe that's usually taken into account. I think it's treated as a horizontal load, and of course it's a load that goes into bearings and substructure.
Okay. We have a question regarding temperature loads. If you have an elastomeric / steel bearing, do the temperature loads create bending forces on abutments?
Okay, we've got a steel reinforced elastomeric bearing, right?
Mm-hmm.
And the steel, that bearing is going to shear. That's its job under temperature expansion contraction. And I believe the conventional way of doing this is to design for the horizontal force represented by the shearing stress, shearing deformation in the elastomeric bearing. Now, once you have that force transmitted to the bearing seat, it's like any other horizontal force. As you go down the abutment, it's going to create some moment.
Okay. And then we're going to have one last question here before we wrap up. I'm on slide 27.
Okay, hang on a minute. Let me go back there.
Okay.
Yes.
Okay. On slide 20,
yeah, good.
yeah, on slide 27, the figure shows 90% of two design trucks and 90% of lane load. Does that apply to only multiple span bridges, or does it also apply to single span bridges?
It was intended to apply to continuous spans, but I believe there are some owners that are using it for longer, simple spans as well. I mean, the owner has choices. Does that answer the question? Because I'd like to tag on to this if I can.
Go right ahead, Jeff.
Okay. You know, the specification generally represents the minimum requirements for design. A professional engineer has to look at the structure and the situation and say, is there more I should do? So there are times when you might have to consider site-specific situations. And the specification points this out, and it has several examples of things you might look at. For example, we have designed international bridges between the United States and typically Canada. And they have other features. They've got toll collection, INS characteristics, customs, and often it's possible to get really unique collections of trucks. And we've designed those bridges for more than the minimum required by the LRFD specification. There have been cases where bridges into port facilities, particularly containerized intermodal situations, have to be designed for more than the minimum required here because of the concentration of heavily loaded trucks. So while we have a very significant, i.e. heavy, HL93 design load, it's still, for an engineer dealing with a unique situation, still incumbent upon the engineer and the owner to look at this and say, is there any chance that more is required here?
Okay. Thank you very much. Unfortunately, I think that's all the time we have for questions this evening.